Okay, so maybe we can start now. So today I would like to start. We need to talk about this RNN, and RNN, it stands for recurrent neural network. So as you can see here, it's RNN. It's a family of neural network which is suitable for learning representations of sequential data like text in natural language processing applications, or a stream of sensor data in instrumentation, for example. So if we have anytime data which are coming in continuous way, should be, if you are measuring temperature, if you are measuring something from a sensor, for example, something in the form of a time series, we can use RNN for solving it. And as you can see, it's RNN, it's very old. In fact, it's from maybe 1940, but because at the time it was very difficult to have enough computational resources, it was very difficult to train those models. But today it's much easier to train those models. And it's very important because they use it for text understanding and lots of applications in NLP. So it's very, very important. As you can see here, this is a form of NLP, RNN. And as you can see here, it's a recurrent neural network. And it's very simple. We have number of nodes, as you can see here. So this is node number 1, for example, 2, 3, 4, and 5. We have number of inputs. Imagine it's X1, for example, X2, X3, and X4. And in fact, X1, X2, X3, X4, this is a number of inputs. It's similar to feed-forward neural network, and we can have in each node here, we can have just weighted sum. So as you can see here, just forget about this recurrent or the feedback, but it's similar to feed-forward neural network. If we need to calculate the outputs, for example, Y1, Y2, Y3, Y4, Y5, for example, how can we calculate those? It's weighted sum of. So I can just say that, okay, omega 1 will be the weighted sum of omega I multiplied by xi. We know this, correct? But before doing this also, we have something here which is a feedback. If you can see here, we try to feedback y back. So I can just call, instead of y1, and I will call it yt, for example, correct? So yt will equal omega I multiplied by xt, for example, x at this time. But we have here feedback signal. We try to feedback the output. When we try to feedback this output, we can call it yt minus 1, for example. When we feedback it, we need to multiply it also by some weights. So we can just add here, for example, I will call it v, for example, multiplied by yt minus 1. And of course, for each node, we need to add bias. So this is the weighted sum in case of recurrent neural network. So it will be omega multiplied by xt, omega multiplied by inputs plus a new set of weights, which is, for example, v multiplied by yt minus 1, correct? Plus bias, and in this case, we will calculate yt. And after that, after calculating this formula, we need to apply it to an activation function. So maybe the activation function, it's ReLU, for example. So to calculate yt, we need to send this one also to the function ReLU. So I can just put it like this one. So it will be ReLU of this weighted sum. So this is, in short, the recurrent neural network. And the recurrent neural network, we feed it with a text data. Could be a text data or a time series data, for example. So we can unfold it to a number of steps, because imagine that we are sending a time series data. So in this time series data, imagine that we have a time series like this one. And I need to build a model to predict the next value, for example. So I can feed it with a single value to predict one value, or I can feed it with 2 values to predict the future value, and I can feed it with 3 values to predict the future value. So we call it, this is a number of time steps, correct? So if the time steps equal 3, so we will have 3 repetitions. If the time steps equal 2, it will be 2 repetitions. So the one in the left here, this is the original RNN, and the one to the right here, it's how it looks like when we unfold it. So in this case, we will apply it to x0, x1. After applying it to x0, we will repeat it for x1, for x2, and so on. So in this case, I can just write my time series like this one. So this is, for example, I can use x0 for predicting x, maybe y1. For example, I can use x0 and x1. I can use x0, x1, and x2. So this is how it looks like when we try to unfold it. So what are the limitations of feed-forward neural network when we try to compare between feed-forward and recurrent neural network? Feed-forward, it can only handle fixed input size. As you can see, if we go back here, in case of feed-forward neural network, if we assume that we don't have the feedback signal here, it can deal with only fixed set of inputs. So we have from, if you have 4 inputs, so it will be x1, x2, x3, and x4, right? Sometimes we need to use zero padding. It can be used to address handling of smaller inputs. If case of feed-forward neural network, sometimes you have only 2 inputs or 3 inputs. We can handle this problem by using zero padding. So I can just set x4 equal 0, for example. So if you are working with a time series and you want to use feed-forward neural network to work with this time series, so I need to divide the time series into bunches or sets of fixed inputs. So maybe the last one, for example, we will have a problem because number of inputs in the last batch, for example, maybe we have only 2 inputs. So in this case, we will use zero padding to replace the other 2 inputs by zeros. So the model breaks, and when input exceeds the fixed input size, it will be a problem. The model size dramatically grows with the size of the input sequence, correct? Because in case of feed-forward neural network, if I have 5 inputs, we can just calculate number. I got some question, I guess, from someone. Yes, okay. So the model breaks when the input exceeds this fixed input size. It will be a problem, we cannot handle it. And the model size also will increase dramatically with the increased size of input sequence. So imagine that I have feed-forward neural network with 10 inputs or with 5 inputs. I'll just try to calculate number of parameters. Number of parameters will grow exponentially, in fact, when you increase the size of the input. Does not require data preparation. Yes, in case of feed-forward, it's something positive. Does not require data preparation, but in case of recurrent neural network, we need to do some data preparation to put the data in the correct format for the recurrent neural network. It cannot capture long-range dependencies between input vectors because it does not have this. It does not have a memory, feed-forward neural network. But in case of recurrent neural network, we have a kind of memory, which is the hidden states. We calculate hidden states, and this hidden states, you can consider it as a memory, which you can try to memorize some long-range dependencies between input vectors. So it can understand the context, for example, and therefore it is very nice to work with when you are working with text data. So this is feed-forward neural network. So we have this problem. It's fixed input size, correct? We need to deal with fixed input size. So if you are working with an image, for example, it should be fixed input size. But we have a problem if you are working with a text, for example. We use the feed-forward neural network for sentiment analysis, as you can remember, for this MD, this reviews data sets. Because some people, they are writing too much, some people are writing too less, for example. So if I want to use feed-forward neural network for doing sentiment analysis, I need to be sure that my sentence has a fixed input size, and therefore we decide the size of the input vector, for example. If you have less, so if someone wrote a review which is very, very short, in this case, we will use zero padding. So we will replace other inputs by zeros. If it's too much, if it's too long, in this case, we will use truncation, so we will try to cut the rest of the text, right? So this is how we deal with the input size. But as you can see here, the input will be a vector, for example. We have a feed-forward neural network, and we have some output. Imagine it's sentiment analysis, so the output in this case maybe should be +1 and -1, for example, if it's positive and negative sentiment, for example. But in this case, we need to have the input vector should have a fixed input size. If not, you need to use this zero padding or truncation, so you can get rid of the extra text. For example, truncation, it can be done from the end or from the beginning, right? So I can, so it's up to you to decide if I need to cut, if the beginning of the text is not important or the rest of the text is not important. We have something called the sequence to sequence, which is something very nice to work with when you are working with RNN. In this case, we have an input, the input will be a sequence, and the output also will be a sequence. And we can use this one for example, text translation, for example. So I need to translate a text from maybe from Nosh, for example, to English. So we should expect that the input will be a sequence and the output will be a sequence as well. So, so it's left to right reading of input sequence. We need to read the input sequence from left to right. So I start by, for example, if the input size is 3, for example, so I will start with the first 3, and after that I will go to the next 3, and so on. And in fact, even if when we are working with images, you can convert an image also into a sequence of input sequence. So imagine that we have this MNIST data set, which is 28 times 28, correct? So it should be possible also to convert this one into a sequence of input sequence. I can convert this image into input sequence by just dividing it into sequence like this one, and just flatten it, for example, so it will be like this one. So in this case, we can work with an image as an input sequence, and maybe also the output will be a sequence. It could be caption. I try to generate a caption for this image, for example, or I'll try to generate a textual description of this image. So in this case, the input will be an image. It will be a sequence of those pixel values. So the input will be a sequence of input sequence of pixels, and the output will be a text, and the text it could be a caption, for example, which we try to generate to describe the contents of the image. So it's left to right reading of input sequence. We need to update the state vector incrementally to represent the syntactic, semantic, and the discourse context from the beginning until the current input. In fact, in case of RNN, when you feed it with an input sequence, you will update something called the hidden state. So we will get, for example, H0, correct? And when you feed it with a second sequence, which is that part, right? We will get another update for the hidden state, which is H1, for example, and so on, until we finish the whole image. H0, H1, H2, in fact, those represent a memory. So it's like H0, it try to memorize something about that part, for example. And H1, we will use H0, we will feed back H0 also to my model, and we will try to get H1. And in this case, H1 will try to memorize something about the whole section here, I mean, including H0 and the new section and so on. So the hidden state here, it represented something like a memory, which try to represent something about the syntactic or semantic meanings of the input sequence. Context discourse will be broken in case, of course, if you would like to use MLP, we will not have this context discourse. It will be broken because if I want to, for example, classify these images, I mean, if I need to do this one with MLP, for example, I need to feed, I will build my model, and each time I will feed one section to my neural network, my feed-forward neural network. So I will feed the first part, so I will calculate the output, and after that I will go to the second part, I will feed it to my model. And in case of the second part, the model does not have a memory, so it will forget the context of the first part. So the context here will be broken. But in case of RNN, we will keep the context by updating the hidden states. So just imagine that this hidden states, it's something like a memory, for example. We need to integrate the current input word into the state. I mean, we do this by updating the states. You can just imagine that the state is a memory. The state can serve as a memory, which allows patterns to be remembered over long-range context. So today, for example, if you are using ChatGPT, for example, you are writing something. I mean, this is ChatGPT. It's generative pre-trained transformers. It's very huge, and it has billions of parameters. So it has the capacity, in fact, to remember the context. So when you are writing something, it will be able to remember the context, and it will try to generate a text which make sense, which is not disconnected. RNN was first introduced. I told you it's very old. Sorry, it was not 1940, it's 1980. I remember I studied this one when I was in bachelor, but it was very difficult to implement. So people go for feed-forward neural network, but for recurrent neural network, we just study it. But for implementation, it was difficult because error bag propagation was not working. It was not easy, in fact, to implement error bag propagation with recurrent neural network. So, but have gained the popularity only recently due to the hardware development that have made them, easy to train. RNN are different from feed-forward neural network because of the recurrent layers, which enable it to propagate information between neurons of the same layer and maintain state between users. This is very, very important of the network. So we have a memory. So the idea here in case of RNN, we have a memory, and this memory, in fact, it's the state. They call it state or hidden state, for example. So this is feedforward in neural network. We apply an input batch here. We have an input. It could be a sequence or anyway, so it's fixed size. So we have an input set, which is a fixed size, and we feed it to each layer, and we will just propagate from input to output, and we will go backward to adjust those weights for this specific batch of inputs, and that is it. We will calculate the outputs, and for the new batch, we will repeat this process. So there is no continuity. In fact, there is no understanding of the context. So imagine that I send a text, and the first text, it's how are you? It will just it will process it, and it will try to generate something here, for example. And then when you feed it with the next sentence, it will just forget all information. It will not be able to keep any information about the first sentence. But in case of recurrent neural network, we will feed it with some input. So this input, it could be apart from a text, for example, a sequence, correct? And we will do this. We will calculate Y, and we will calculate the hidden state. This hidden state, it will understand, or it will try to memorize something about the context. When we first feed the first batch of inputs, it will update H, so we will have H0. The next batch, it will update H, we will have H1. And as you can see here, also we feed back those hidden states. Do you see? We feed back those hidden states. So each time we will update the hidden states using the input and using those hidden states. I mean, when we calculate H here, it will be a function of X and function of H. So we can just say that HT will be function of HT minus 1, correct? And XT, for example, right? It will be like this one, if you want to write it as an equation, for example. So the most simple RNN, it's called vanilla RNN, or simply, you can just call it simple RNN. And the vanilla RNN model uses a standard perceptron layer. It's a very, as I explained it last time here. As you can see here, it's a standard perceptron layer, right? With nonlinear activation, we have nonlinear activation to achieve the recurrent state input combination function. So we have this state input combination. We try to combine states and inputs to calculate the new states and so on, right? So there are several versions of this RNN with stronger representation power. So this is the most simple one, which is simple RNN, but also we have something called GRU, for example. We have LSTM. So there are lots of variants of those recurrent neural networks. In this vanilla, we will study vanilla in details because it will help us to understand how it functions. So vanilla RNN calculates an output sequence. We'll try to calculate the states. You can call it output sequence because, in fact, here we calculate the output, but outputs equal those states. So we will try to calculate H1, H2, those states, and Hn given an input sequence. And in this input sequence, it will be X1, Xn. The size of X1 and Xn, it's a vector, in fact. So this one, it's a sequence. Recurrently from the initial state, we calculate first initial state H0. We need to initialize this initial state. It could be with maybe some random values of zeros, for example, where HT is a vector. T belongs to this 1 and n until n is calculated according to the previous state HT minus 1. So we calculate HT based on the previous state HT minus 1 and the current input XT, as I wrote it last time. So I can just write it as a function. So HT will be a function of XT, for example, and HT minus 1, right? So we have this kind of recurrent here. If it's a feedforward neural network, we will remove HT minus 1 because in case of feedforward neural network, we calculate the output as a function of input. But in our case here, we will calculate the output or the states as a function of the current input and the previous states. So the equation is very simple. It can be written in this way. HT will be this function. This function, in fact, it's a activation function. If you are using ReLU, for example, you can replace it with ReLU. But the most important here, we just calculate H as a function of the previous state, HT minus 1 multiplied by V, or by omega H, for example, plus omega X multiplied by XT plus bias, as I wrote it in the first part here. Yes, exactly the same here. So this graph, it will be easy in fact, it will just give you good understanding how it works. So we try to calculate YT or HT as a function of inputs. So we need to multiply those inputs by weights. So it will be omega x multiplied by x plus omega x multiplied by HT minus 1 plus minus. That is it. So so you just need to define here. You just need here to define number of perceptrons, number of units, or number of neurons. So this is the most important, and of course how you will structure your inputs, because number of repetitions here, it will be the number of time steps which you want to use in your time series. So F is nonlinear activation function such as the hyperbolic tangent, for example. This is the original version of RNN. They use hyperbolic tangent. Omega H and omega X and the bias are model parameters which are shared among different time steps. It's just the model parameters. RNN versus MLB. MLB, it's multilinear perceptron. RNN looks very different from MLB and CNN due to the current recurrent time steps. We have this, I mean, because we just unfold it or we just update it one time each time step, right? In MLB, the output from the lower layer is fed as input to an upper layer. So this is MLB. We feed the inputs here and we go from lower layer to top layer, right? Like this one. In case of RNN, the output of a network is wired back as input to itself. We have this kind of feedback here. We can say that it's feedback signal, for example. So we have a kind of feedback. So we apply X, which is a vector, correct? We start with H0. It's just initialized with random small random values, for example, and we will go we will go forward and we will calculate H1. Once you calculate H1, so this is the initial value here. We will calculate here H1, and we will feed H1 to the model, and we will repeat this process in the time steps, right? We will repeat this process in the time steps. So this is the difference. When you try to unfold it, it will be like this one. I mean, this is the original structure. So we have X, we calculate H using X, but just remember that we initialize H with, because we need to have initial values for H here. So we will start with initial value H0, right? As you can see here. So H, in fact, we need to calculate H as a function of X and H0. So it will be omega X multiplied by X plus omega H multiplied by H0 or by H plus bias. I mean, this is the whole process. But we can unfold it into some time steps. When it's unfolded, it will be like this one. This is the original equation, we know it. But when you want to unfold it, it will be like this one. First, I need to calculate H1 as a function of X1 and H0. I need to calculate H2, which will be a function of X2 and H1, the previous state, and so on. So if you want to write a more general equation, it will be like this one. So we need to calculate Hn as a function of Xn and Hn minus 1. And the equation is very simple. This is the equation from the perceptron, right? So the parameters here, if you want to calculate number of parameters, because we know this very well from CNN, for example, so we just need to decide omega H, and the omega H, it will be number of states. So we need to decide how many states here, how many hidden states. I mean, number of hidden states will be equal to number of perceptrons, right? Number of hidden states will be equal to number of perceptrons. If we can go back here, because we have one hidden state from each perceptron. So if you decided that I will have 5 neurons, for example, with 5 perceptrons, so in this case, number of hidden states will be number of perceptrons. You don't need to decide number of hidden states, because number of hidden states equal to number of perceptrons. Okay. Yes. And number of omega. What is the dimension of omega X? Dimension of omega X. It's based on X, right? So how X is represented? As I told you, X is a vector of number of input values. So it's based on, in fact, the number of steps, number of time steps. Because if you have a time series like this one, so I need to know how many previous values will be used for predicting the next value, right? So you can say that maybe someone he want to use 3, for example. So in this case, it will be 3 months. I need to use previous 3 values for predicting the next value. So number of repetitions here, it will be 3, for example, if I will use 3 values, for example. But x itself, how x is represented, right? Is it single value or multiple values? So, so the steps can be written as one function. So we need to calculate hidden states. So h will be RNN of x, right? Because we have this feedback loop. So we try to feedback h into our RNN for calculating, for updating each hidden state. So the initial hidden state h0 can be set to 0, or it can be defined as a randomly initialized parameter. So we can define it to zeros or some small random values. The final vector hn can be used for representing x from 1 to n. So for example, I have this text, sentiment analysis, for example, and I have a review for a movie, for example. So I have x from 1 to n. I don't know how many words. It could be 20, it could be 100, for example. So imagine n equal 100. So in this case, at the end, I will calculate h at step 1, or just I will calculate h, which will be representing all my input text, right? So at the end, this h, it could be +1 or -1. So it will be positive if the text from x1 to xn has a positive meaning or a negative meaning, for example. So RNN are trained using unfolded representation. And in this unfolded representation, we need to use different version of error backpropagation, which is called backpropagation through time. It's a BPTT. It's called backpropagation through time. The training is identical to MLP, except that number of layers is dynamic to the input, and they can be very large. So because we have number of repetitions or number of time steps. RNN are subject to gradient exploding and vanishing problems. This is a very large problem here, in fact. And maybe it was one of the problems that RNN was not attracting too much attention because of those gradient exploding and the vanishing problems. But of course, in advanced versions of simple RNN like GRU, for example, and LSTM, for example, it does not have this problem. I want here to compare between simple RNN and RNN, for example. Simple RNN, we explained it already. We need to calculate the state, we need to calculate H, right? The states. So it will be, we will use this activation function, which is hyperbolic tangent. So if we need to write this equation, so H of t equal hyperbolic tangent of omega. I don't want to use this one because we use here omega h. So it will be omega h multiplied by ht minus 1 plus omega x multiplied by xt plus minus, right? B of h. B of h because the number of hidden states equal to number of B here. It's not a single value. In fact, it's a vector, right? It could be B1, B2, B3, B4. So it's according to the number of units which you are selecting here. We will go back again to our representation like this one. So this is our recurrent neural network. We calculate h. So we have x1, x2 until xn. We will calculate those h, for example, because it's wrong representation. But anyway, it's like this one, for example. But we need to feedback this one here. Just feedback those ones back here. So this is the representation of the simple RNN. It's very, very simple, yet also still efficient. We can use it for solving very nice problems. So simple RNN, it's very easy to implement in Python. In case of RNN, it's the difference. The only difference here, we calculate YT here as a softmax of HT, right? So it's as a softmax of the hidden states. But in case of RNN, it's a little bit more complex. So HT will be the same. We need to calculate HT first, those states, similar to our simple RNN. We need to initialize HT to 0 vectors or small random values. But in case here of YT, it will be softmax of this weighted sum. So it will be omega multiplied by h plus p, right? But in this case here, it's just softmax of HT directly, right? Because we need to calculate the probability of the next word, for example. So we need to have the last layer or the output layer. It should be softmax layer because we need to calculate the probability. So the difference between simple RNN and RNN is that Y of t, it will be softmax of H of t directly, right? It will be like this one, correct? But in case of RNN, it will not be softmax directly of H of t, but it will be softmax of O of t, and O of t, it will be V or multiplied, or it will be, for example, V multiplied by HT plus bias, right? So it will be like one perceptron. So this one, it will be like another perceptron, another layer. Here we have only one layer. Here we have two layers. So in the first layer, we will calculate H of t, and after that, we will feed H of t to the next perceptron to calculate Y of t, right? So if I want to represent it like this one, I can make it like this one perceptron. So, but just imagine that it's not a one perceptron, it's maybe an array of perceptrons. So we will have here X of t, correct? We will calculate here H of t. We will feed back this one back here, correct? So HT of -1, we will feed it back into here. We will calculate this weighted sum. We have here bias. And after calculating H of t, we will feed back it to another perceptron. So this perceptron, it will calculate this weighted sum, add another bias here to calculate Y of t. So it will be like this one. So we have two layers, but in case of sample RNN, it's only one layer. So H of t, it's this is when it's unrolled. I mean, if you want to unfold it for time steps equal 3, for example, when we have those time steps equal 3, so in this case, we will feed it with xt, H of t, we will calculate ht plus 1, we have bias h, we will repeat this process 3 times, and at the end, we will have, this is about RNN in fact, right? And at the end, we will have this dense layer. This one, you can say that it's dense layer. So we need to define I don't know, WH by, or you call it WY by, and we will calculate this output, right? Okay, so the mathematics, we explained already the mathematics of this RNN. It's simple. We will need to calculate H of t, so it will be phi of omega multiplied by x plus omega multiplied by h t minus 1, of course, plus b of h, for example. And we need to calculate the output, which is the probability of the next character, for example. So it will be the softmax layer of omega multiplied by h plus b. This is for RNN. But if you want to replace this one for simple RNN, it will be directly softmax of h and t. Okay. I mean, those model parameters, I mean, you just need to define. I mean, no problem. I mean, we just forget about this one. We will explain this one later for maybe simple RNN. So applications of RNN, we can use it for image captioning. For example, image captioning, it's one-to-many application, which means the input will be one image, and the output will be a text or a sequence of sequence. So it's like one-to sequence, one-to-many or one-to sequence, because in this case, the input will be an image, and I want to generate a textual description of this image or a caption of this image. So for example, I will feed it with an image, and in this image there is, for example, an elephant, for example, drinking from a lake, correct? So I want to find a description for this image, or the caption, for example. So it's image captioning, which is one famous application. So in this case, it will be one-to-many, because we will feed it with one image, and the output should be a text. So the output will be a sequence, right? In case of time series predictions, it's one-to-one. It could be one-to-one or one-to-many, in fact, correct? In fact, because I can feed it with one value and I want to predict the future value, for example, or I can feed it with a sequence. In fact, I can feed it with 5 values, because I can feed my model with the temperature of the last 5 days, for example, and I want to predict the temperature for tomorrow, for example, right? So if I want to predict temperature for tomorrow, maybe I can send, if it's one-to-one, for example, so I will send it the temperature of today, and I use temperature of today to predict temperature of tomorrow, correct? Which might be misleading, because maybe it was raining, it was very cold yesterday, today it's hot, and because today it's hot, the model will predict temperature tomorrow is hot, which might not be correct. So in this case, if I need to reduce uncertainty and the prediction error, maybe I will feed it with two values, temperature today and the temperature yesterday, to predict temperature tomorrow. Or maybe someone else will say, no, I will feed it with the temperature of the last 3 days or 5 days or 4 days or 5 days to predict temperature of tomorrow. So this is the time window. And this time window, it will be it will reflected into the number of steps or number of repetitions. In case of NLP applications, for example, sentiment analysis, it will be many to one, because in this case, I need to feed my model with bunch of text, and I want to calculate the sentiment, or it's positive, negative, for example. So I need to just predict if this text is positive or negative. So the input will be a sequence of text, and the output will be just a +1 and a -1. So it's a binary classification problem. So it's a many to one. In case of machine translation, which is the most complex one, for example, or text generation, for example, so we need to translate input between different languages. So it will be many to many. I need to translate Chinese into English, correct? So the input will be a sequence, and the output will be a sequence. So in this case, we call it many to many. So this is one-to-one RNN. We can use this vanilla neural network, which is simple RNN, and it's used for generating machine learning problems that has single input and a single output. Use today or current stock price, for example, to predict tomorrow or future price for investment decision, for example, and you need to prepare your data in the form of one-to-one, right? So in this case, I need to convert, because this is a time series, which is just a set of values over time. So in this case, I need, for example, to convert it into this form, right? So it will be like X and Y. So I will use today temperature, just shifting it one step. So I will use all values. I mean, if this is time, for example, it's from 1, 2, 3, 4 of the week, for example, 5, 6, 7. So I will use those values here for predicting the second day value, right? It will be 2, 3, 4, 5, 6, 7 values. So it's the same values, in fact, but I need to convert it into this form, and I need to feed X and Y to my model for training process. And after that, I will use it for testing. So if it's time series, how can we do it? We cannot shuffle a time series, because if you will shuffle the time series, you will destroy the context of the time series, right? So I just need to divide it like this one. Maybe from the beginning to that place, that part, it will be used for training. And that part will be used for testing. We cannot shuffle. Remember that in time series, you cannot shuffle it. So I will use that part for training, and I will use that part for testing my model, but I need to put my data, in fact, in the correct format, right? Because X here, it is a stock market, maybe in US dollar, for example, stock value, for example. So so the price today was this value, tomorrow it will increase to this value or decrease. So I want to decide, I want to try to predict the stock price tomorrow, for example, so I can put more money or less money in that one. Should I decide to buy more or sell it? Because our predictions said that maybe the stock price tomorrow it will go down. So in this case, maybe it's better to sell it today to avoid any loss. So in this case, we need to, if it's one-to-one, so I need to put it in that format. But also I can work with this one as many-to-one, in fact, right? So as I told you, I can have a larger time window. So I can just say that, okay, I will use, because it's a smart, to use the last 5 days. I mean, the price of, because if it's a Friday, for example, I cannot make a decision Thursday evening, for example, based on Thursday value. Maybe it's a smart to use the whole week values. So I can increase the time window in this case. And in this case, I need to put the data into that format. So if you will use the last 5 values, so it will be like, so I will just write it like this one. So it's X1, X2, X3, X4 to predict X1, X2, X3, X4. I will use those values for predicting X5, correct? So I will call it Y, right? And I will use, after that, I will shift it by 1. So I will use X2, X3, X4, X5 to predict X6. I will use X6, X3, X4, X5, X6 to predict X7. So I need to put my time series in the correct format. So in this case, in fact, the time steps, it will be 4 time steps. So number of repetitions when I run my RNN, in fact, we need to do this repetitions 4 times, right? Because the time steps here equal 4, for the size of my time window equal 4. So when you are working with a time series, if I can use RNN to predict a future value using the most recent value, correct? So it will be 1-to-1, but at the same time also, I can use this one multi or mini to one. When it's mini to one, it will be like this one. So I need to increase the size of my time window. And in this case, I will use the most recent 4 values for predicting a future value. So you need to do this preparation for your data before training your RNN model. Image captioning, it's very simple because it's 1-to-many, right? So the input will be 1, correct? Which is a single input, it's just an image. And you need to convert this one into many, into a sequence. We call it 1-to-many. So the output will be multiple outputs. We will get those multiple outputs, and this multiple outputs, it could be a description of your image, for example. So it's a dog catching a ball in mid-air, for example. So I need to have a data set to train the model, and this data set, it will be number of images with a caption, correct? So I need to get some images, and someone should write something. Okay, this is the caption. This is the caption of this image. So this is my training data set. And after doing this, I will test my model with that. So I need to get a data set, right? We need to convert it into training and testing. And after doing this, we need to test my model with a new image, for example, and we will see if it can really generate a text which is describing the image, or it's maybe random text, for example, right? So image captioning also, it's very important because it could have also very nice applications, correct? So maybe some people who have some vision impairment, for example. So in this case, I can just help them. I can build a model which can give them a description of the surrounding environment. In case of NLP,
excuse me, can I ask a question?
Yes, please.
Sorry to interrupt you. I wanted to ask a question regarding the previous slide where this one.
Yes.
I was actually doing something similar in my project in the past, and instead of recurrent neural network, I simply used lag features. So to create these x1, x2, x3, x4 to predict x5, I simply added lag features to my input data, and you can do this. I mean, this way you can use a normal feed-forward neural net, or you can use a random forest or whatever. Is there a advantage to use recurrent neural network to get this kind of repeating recurrency to progress?
Yeah, because if you will use here feed-forward neural network, I will use this bunch of values for predicting x5, correct? I will use this sequence for predicting x5, and I will feed it with another set from x2 to x5 to predict x6.
Exactly.
So maybe the model, because this feed-forward neural network, it does not have this hidden states. So maybe
then
it will not.
You will. What I mean is that you will manually create the hidden states before training, and you will add it to the data.
So you will create a hidden state and feed it to this one.
Yeah, you will create hidden states for all of the input data and add it. So it's kind of a synthetic data augmentation.
Yeah. I mean, it should be fine. Yes, should be okay, I guess.
So then you can in practice do the same thing without the RNN.
Yeah, this is correct. But the advantage here, in case of RNN, if you are working with a text, you don't need to worry about the size of the input text, correct? But it's the same here also.
I was just wondering if I can see that RNN is much more elegant and the natural way to do this automatically, and you don't have to work that much to create
yes
the lag features. But I never thought about this, that it's actually very similar, and I was wondering.
It's very similar because as you can see here, it's a feed-forward. It's like feed-forward in neural network. I mean, you see, this is a model, correct? So it's simply feed-forward, right? But we just, as you did, we have this lag feature, for example, and you have this kind of feedback to the input again. So you just calculate those lag features and you feed it to the model. So it's exactly the same. So it's like feed-forward in neural network, right? Because we just feed inputs and we calculate the states or calculate the outputs, because in fact it's the states or the outputs and they feed it back again to the model. So it should be the same. So it's just a way to try to get a memory or to get some information from historical values, from previous values. So maybe it would be nice if you can, if you still have this code, for example, you can try it again with the recurrent neural network and try to make comparison between the performance. Maybe if you have better, you can check if you have better accuracy or not. So yeah. Oh, any other question, please?
I had a question as well with the previous example that you had with the predicting, this one.
Yes.
What do you mean exactly when you say that the network can take several input lengths? You mean it can take like variable time steps or the number of...
No, I mean here we have the input is one it's just one x, correct? And the x here it's a float number, correct? It's just a float. X here it's not a text. X it could be a text if you are working in time, if you are working with text, for example. So I can say that X is a word, correct, or a sentence, right? So just x1, x2, x1 it could be just one word, for example. It could be a sentence, for example. But in case of this time series, it's very simple. It's just a float number, right? So hx here it's a float number, but when you use this time window, for example, you can say that I need to use the most recent 4 values for predicting a future value, for example. So in this case, I will use from x1 to x4 to predict x5, but each x is float value. So in fact, in this example, if we need to use RNN, it will be like this one. So I will just feed, if we need to unfold it, for example. So I will feed x1, correct? I will feed in the first step, I will feed x1. And of course, we have this the hidden state is initialized to 0, for example. So I will use this one, and I will calculate h1, right? So I will just have this h0 here, like this one. And I will repeat this process. I mean, this is one step. So first, we calculated h1 using x1 and h0. I will repeat this process. I will feed, in the next step, I will feed x2, correct? Sorry. Oh. I will feed x2, sorry, because maybe we need to write in another place. So I will feed x2, and I have h1, for example, now. So I will feed h1, correct? And I will calculate h2. I will repeat this process another time using x3, calculate h3. I will repeat this one for the 4th time, and in the 4th time, the input will be x4. And we will calculate, we will use h3 for calculating h4. Once you have h4, sorry, I will use this h4 for calculating x5, right? So how many repetitions? So each time, I mean, if I need to predict x5, you need to do 4 repetitions because the input sequence is 4, right? But the size of the input, I mean, the dimension of the input, it's just 1 because it's only one variable. It's float number. So I will just use x1, h0 to calculate h1. I will use x2 and h1 to calculate h2. I will use x3 and h2 for calculating h3. I will use x4 and h3 for calculating h4. And once you calculate h4, you will calculate this you will use this h4 for predicting or for calculating x5, right?
So when you say, I think what I don't get is when you say that the RNN can take variable length for input in comparison to other models we've seen in the feed-forward network in particular, do you mean that x1 can have a different length than x2? Or do you mean that, like, what does it mean, this variable length that the RNN can take? Because as far as I can see, the vector that we feed it to get x5 or to get x6 has the same length. So I don't understand what's this variable length.
It's a variable length. So for when we are working with a text, for example, so when we are working with a text, imagine that the text is a sequence of inputs. So this sequence of inputs, it could be short or it could be long, right? You don't need to do too much working with the data to fix it. So maybe someone, he will write one sentence or 2 sentences to describe a movie, for example, or someone else, he will write one full A4 page, for example. So we don't need to take care about this, because the most important for us is that we will process the text one sentence by one sentence, but I don't care about how many sentences we have. But
Okay.
of course, I need to fix. I mean, what we will feed to the model, it should be fixed. I mean, we need to fix it. But how many repetitions? I mean, I will do this repetitions each time for calculating the next word. So imagine that I have a sentence, and from the sentence, I need to predict the next word, for example. So I will do this, but I don't care how long my text, right? We don't need to worry about this.
Okay, thank you.
Yeah. So in case of NLP, sentiment analysis, so we will have some multiple inputs, and the output will be, I mean, we know this because we did that last time using NLP. Do you remember? We used NLP, multi-layer perceptron for sentiment analysis last time. So, but if you can remember, in case of multi-layer perceptron, we feeded the whole text one time to my model. Do you remember it? We did that last week, 1 week before. When we use MLB for sentiment analysis, I cannot divide the text. If I have a text like this one, when it rains, look for rainbows, for example. When it's dark, look for stars. This is a text I need to feed it to my model. So if you will use MLB, I need to convert this one. I need to use word embedding, and I need to convert this one, for example, into one vector, correct? And I will feed this vector to my MLB. So in this case, we need to use zero padding maybe, because if case of MLB, the input should be fixed. So I need to apply the whole text one time to my MLB. So I need to make some difficult decisions. For example, I need to decide how many words we will use. In case of MLB, we decided. Do you remember? We said that, okay, we will select a dictionary of 20,000, I guess, I don't remember, 20,000 words, most popular, and I need to decide that maybe the length of the input will be 100 words. So I need to select the most popular. I need to have this word embedding or one hot encoding, and I need to provide my model with one fixed vector representing this text at once, right? I will not here work with, I will not go through the text like in CNN, for example. In case of CNN, we scan the whole image from left to right and from top to bottom. In this case also, we can do the same. We will process the text from left to right, but I don't need to put the whole text into one vector and apply this vector one time to my MLB. If I need to use MLB for sentiment analysis, I need to convert this text into one vector, correct? But we will have some hard decisions because, as I told you, if one wrote very short review, for example, we need to use zero padding. So maybe the first part, I will have some word index here, maybe something here, 1001 something, but I cannot process the whole text because this guy, he wrote too long text. So I need to do some truncation. I need to cut. I need to ignore some part from the review, for example. And if it's too short, I need to use zero padding. So the rest of the vector will be just zeros, for example. And I will feed this vector to my multi-layer perceptron. So in this case, multi-layer perceptron will have huge amount of parameters, correct? And the chances to overfit will be very, very high because the input must be fixed. But in case of RNN, we don't need to do this because all what I need is just to decide the input size, right? I mean, how the input size will look like. Maybe I need to send each time 3 words, for example, correct? And I will just continue scanning the text each time. I will byte new word and go across the whole text, right, until we finish the whole text. So in case of RNN, we don't need to use this truncations or zero padding because the input size is not fixed, right? Of course, we have this. You need to decide how many words in each repetition, how the input vector will look like, but you will scan the whole input sequence, right? So in this case, the number of parameters in this RNN does not depend on the size of the input. But in case of MLP, multi-layer perceptron, number of parameters will increase exponentially if the size of this fixed input vector will increase. Do you understand me? So this is the difference. In case of MLP, if we are working with a time series data, for example, or if we are working with no time series, I don't want to mix it. If we are working with a text here, I need to convert this text into a vector, and this vector must be fixed. So imagine that the size of this vector will be 1000. So in this case, 1,000 words, for example. So I need to convert those 1,000 words into one hot encoding, for example, or I need to convert it into a vector. So in this case, the input will be all time. It will be 1,000. All time will be 1,000. If someone wrote a long review, I need to use truncation because I need to shrink it into those 1,000. And if someone wrote less text, for example, in this case, I need to fill fill the rest by zeros. So we need to use zero padding or we need to use truncation. But anyway, for my MLB, the input will be 1,000 all time. And I need to convert the whole text into this vector, apply this vector to my MLB, and try to predict the sentiment, for example, it's positive or negative text. But in case of RNN, we will not do this. We just build a model. A number of parameters in this model will not depend on the size of the input, right? Because I will just do scanning from left to right until we finish the whole sequence of inputs. But the number will not increase. So if someone has a long text or short text, my model will be fixed, no problem, because it was designed like this one. It will just scan the text, and each time, how can we keep an eye on the context by updating the hidden states? So I will give it the first sentence, and I will update H. I will calculate H1. After that, I will give it to the second sentence, for example, and I will update H. So I will calculate H2, and I will repeat this process until we finish the whole sentence, for example, or the whole paragraph. And at the end, I will get HN, and I will use this HN for calculating the sentiment analysis. Is it positive or is it negative? Maybe using softmax layer, for example, at the end. So this is how it works. But if we need to do this using MLB, I need to convert this text into a fixed input, an input vector of fixed size. But we will have some harder decisions because maybe the text is too long or too little, for example. So in this case, we need to use zero padding or truncation, for example. So in this case, we will lose some information. First of all, we will lose some information because I need to use truncation, for example. We will not be able to process the whole input sequence, for example. And when we convert it into this fixed dimension, we will have this sparsity something problem because maybe for some reviews, we will have too much zeros. It will make a problem for my model in the training process. And maybe also if the size is 1,000 or if it's 20,000, in this case, the number of parameters in my model will be very high, really. And the chances to overfit will be very high unless you have enough large data set for training this large number of parameters. So this is many to one RNN. So the input will be maybe a sequence, maybe it's multiple inputs. Those multiple inputs, just imagine it, you have a text, you will divide it, you will break it down into words, for example, or into some sentences. And each time you will feed maybe 3 words until you finish the whole text. So it will be multiple to 1. Each time you will calculate H. Here I will get H1, I will calculate here H2, and in the last step here I will calculate H3, for example, and I will use this H3 for calculating my predictions, my sentiment, right? In machine translation, it's many to many, so it will be multiple inputs and multiple outputs. The input will be a sequence of text, maybe in Spanish, and the output should be a text also maybe in Chinese or French or Germany or whatever. So it's many to many. So in this case, RNN will take a sequence of inputs from a source language, and it will generate a sequence of outputs of a target language. And of course, if you need to train this machine translation system, you need to have also a larger data set where you have input text, and the output text should be in a different language. This is when you unfold it, for example. So it's just more explanation, which might not be very important. So this is RNN, in fact. So we will calculate those states because I got it from somewhere else. So I'm not using the same symbols. So it's just this one. We will calculate H using input and HT minus 1, right? And after calculating this HT, we will feed it to another softmax layer, for example, for calculating the output, right? So this is RNN, in fact. So this is a probability. It could be the probability of the next character. This is unfolded. When you unfold it, it will be like this one. So we will do some, maybe it's important to get the output or not. So this is, yes. In fact, it's a simple RNN also. So you will do 1 repetitions for calculating H of t for H1, for example, you will do another repetition for calculating H2, another for H3 until you get Hn at the end. And at the end, you will just feed this Hn to a soft layer for calculating maybe probability or predicting sentiment. So the input sequence will be like this one, and the output, if you want to get output sequence, so in this case, you need to get access to the output at each time step, right? Sorry for this. So if you want to do sentiment analysis, I don't need to get those hidden states. I don't need to calculate those intermediate values because it's not important for me, right? So in this case, it will be many to one. If you focus only on the last hidden state, Hn, for example, so it will be like many to one. But if you want to make it many to many, so in this case, we need to get access to those intermediate values. So each time when we feed it with a word, it will generate another word, and we will repeat this process until we translate the whole text. So simple RNN, we need to define, I mean, this is very important. We need to define number of units. So this number of units, it's a positive integer, which is the dimensionality of the output space, right? This is the number which we need to decide, right? So number of units. So the number of units is the positive integer, which is the dimensionality of the output space. So if the input is, if it's many to many, for example, so the input will be 3 words and the output will be 3 words. So in this case, we need to define those number of units or number of perceptrons. Input, it's a 3D tensor with a shape batch multiplied by time steps multiplied by features. So this is the most critical part. You need to put your inputs in that format. So it should be in the form of a 3D tensor with a shape of batch multiplied by time steps multiplied by the number of features, right? So if we are working with, I need to use most recent 5 values for predicting temperature, right? So in this case, I need to see how many data points we have. How many, imagine that I have 100 data points. And if the time steps, if you want to use the recent 3 time steps for predicting future value, future value, for example. So in this case, the number of features will be 1 because I have only temperature. It's 1D. The time series, it's in 1D. So in this case, the number of features will be only 1, right? And I will use the most recent 3 values for predicting future value, for example. And as a batch, you need to convert it into, as we did in the table last time, and you need to see how many batches you have, because this one will be 1 batch, this one will be 1 batch, and so on. So, so the input shape, for example, if the input shape is 3 and 3, so in this case we have 3 words, maybe A, B, and C, and therefore the number of time steps equal 3. And the RNN will be unfolded in 3 times. For each word, we pass the word embedding of size 3. So if you have, for example, A, B, C, for example, and each word is, so I have like a sentence, and the sentence consists of 3 words, A, B, and C. So in this case, the time steps will equal 3. And I will apply A first, calculate H1, and after that I will apply B, and I will apply C to calculate H3, for example, and at the end I will use H3 for maybe predicting the next word, which is B, right? And the number of features, it will be how you represent each word. If you can represent, if A is float number, it will be just 1, right? If A is represented using one-hot encoding, for example, so A will be represented by a vector like 1, 0, 0. So in this case, number of features will be 3. So A will be 1, 0, 0, for example, B will be 0, 1, 0, for example, and the C, it could be 0, 0, 1. So we use this one-hot encoding. So in this case, as the dimension of input dimension will be 3. So when you use this number of units equal 10, which means that the hidden layer has the hidden layer has 10 units, or we calculate 10 hidden states and the 10 outputs, right? If you want to get access to those intermediate values, could be 10 outputs or just. So this is very simple implementations in Keras, for example. So model equals sequential API. We need to add RNN layer. It will be simple RNN. You need to define number of units here, and this is the input shape, right? This input shape. When it's a 3, 3, it means you have 3 time steps, and in each time steps we will feed one vector, one feature, and this one input, and this one input will be represented by 3 features or by 1 feature. If it's a float number, it will be, this number will be 1. If it's a word, and this word we cannot feed a word, we need to represent this word by word embedding or by one hot encoding. So if you will represent A by this one hot encoding, so in this case, the input dimension will be 3. So this is simple RNN. I mean, 10 units means we will calculate 10 hidden states, right? So number of hidden states here will be 10. And at the end, because we calculate, we use those inputs. I mean, do you see here? We have here 3, maybe I have 3 words, A, B, and C, and I try to predict, I need to use softmax layer at the end, and I will feed the input, the output from this RNN to this dense layer, softmax layer, maybe to predict maybe the next word, for example. So the outputs here, it will be, for example, 3, because I need to see, because I have 3 inputs, A, B, and C, and I need to see what is the next word. Is it A, B, or C, right? So if it's A, so maybe the output will be like this one. It will be like 100, correct? Or it could be 010, or it could be, for example, 001. For example, one number of units of the softmax layer equal 3. And this is the equations. We understand those equations, right? We understand those equations now. So number of parameters of simple RNN. This is how it works. For example, so if you have number of units, if you have 10 units, for example, in this simple RNN, for example, so we have input, which is number of features here, and we feed it to each perceptron or each unit. To calculate HT, it will be this weighted sum of omega x multiplied by x plus omega h multiplied by h plus bias. And after that, apply the activation function, which is hyperbolic tangent, to calculate HT. So we will do it for calculating H1, H2, H3, H4, and so on. So number of hidden states equal to number of units. This is clear. So we just need to define number of units, and number of hidden states will be equal to the number of units. If you want to calculate weights of this model, so it's this recurrent weights, and we have recurrent weights. This is the recurrent weights, and this is the input weights, right? So this is the recurrent weights, this is the input weights, and we have bias. If you want to calculate number of parameters, so first I need to calculate omega h. How many of those omega h? Omega 1, omega 2, omega 3, and omega n, for example. How many omega x input weights? Those input weights, it will be based on number of units multiplied by number of inputs. So if I want to calculate omega x, so it will be number of units multiplied by the input dimension of x, right? So if I have x1 and x2, if I have 2 inputs, so it will be number of units multiplied by 2. If I have 10 units here, it will be 10 multiplied by 2. And what about number of weights for recurrent weights? It's easy, because it's just equal to the number of units, right? Number of units plus bias. How many bias? It's a number of units. So if I want to calculate those numbers, so it will be for those weights, it will be number of units multiplied by number of inputs, right? So if I have, okay, number of units. Sorry, it's because I have 10, and I will have this recurrent weights, because I will feed back each state, each hidden state. So how many weights of this omega? So it will be 10 multiplied by 10, right? And for the input, it's according to number of features. If I have 3 input features, for example, so it will be 10 multiplied by 3. Plus bias, how many bias? It's a number of units plus number of units. So this is how we do it. Don't worry about number of repetitions, because number of repetitions, it's don't care about number of repetitions, because number of repetitions, it will impact number of activations, but not model parameters, right? So number of repetitions, it will be this number, right? It will be this time steps, number of repetitions. So if time steps equal 3, because each time I feed it with a sentence, and the sentence consists of 3 words, for example. So number of steps will be 3. If it's a time series, as we did before, and you said that I want to use the most recent 3 values for predicting a future value, so in this case, number of steps will be 3. So number of steps will impact the number of activation. I will do one activation. I will calculate H1. I will do another activation to calculate H2, another activation to calculate H3, and so on. So those number of steps, it will impact number of activations or calculations, but it will not impact number of parameters. And therefore, as I told you before, if you are working with a time series, or if you are working with text, for example, it will not impact the model parameters, but it will impact the number of activations. But if you are using MLB, no, it will impact number of parameters. Maybe number of parameters will explode, and the model has higher chance to overfit because the input dimension is very high. But in case of recurrent neural network, it will not impact number of parameters, but it will impact only number of activations. And it's similar also to CNN, because in CNN also, if the image size is 512 times 512, we will have number of activations. If it's 124 times 124, it will not impact number of parameters, but it will impact the number of activations. Please, if you have any questions, just ask it before going forward. So here we need to define our NN model in Keras, for example. So I just use a sequential API, for example, and I use one simple RNN layer. I need to define this number of units. This is number you need to decide it, right? Because this one, it will impact, it will be the dimension of your hidden states. How many hidden states you want to get, right? 10, 5, 4. So this is the number of units in the hidden layer, or the number of hidden states, or number of outputs. So it will be number of hidden states or number of outputs in case of RNN, for example. So if you want to, which means here, how many outputs I will fit to the next dense layer, it will be 10. Because from these units, I will calculate 10 hidden states or 10 outputs, and I will fit these 10 outputs to the next layer, which has 3 units. So number of parameters in this, I will just start with this dense layer. Can you calculate number of parameters of this dense layer? It will be 10 multiplied by 3 plus 3. 33, right? Because number of outputs, I mean the output shape from this simple RNN, it will be 10, because we decided that number of units equal 10. So output shape will be 10. And here number of units equal 3, so the output shape from this layer also it will be 3. So number of parameters here, it will be 10 multiplied by 3 plus 3. We understand it now. So those 33, it will be 10 multiplied by 3 plus number of bias, which is 3. So it will be 33. Now we need to calculate number of parameters of this simple RNN. How will we do this? I have 10 units. Those 10 units, it will represent 10 hidden states. And we will feed those 10 hidden states to my input one more time through omega, through weights. They call it recurrent weights. So how many recurrent weights? It will be 10 multiplied by 10. Input weights, how many input weights? So we need to check this input shape, right? Not this number, because this number it's number of repetition or number of sequence. So this one will be number of iteration. We need to check, this is the most important number here, 3. So in this case, I have 3 inputs, right? And the 10 units. So how many input weights? It will be 10 multiplied by 3. So it will be 10 multiplied by 3, right? And how many bias? Because I have 10 units, so I will have 10 bias. So if you need to calculate number of parameters of the simple RNN, it will be 10 multiplied by 10, which is number of recurrent weights, plus 10 multiplied by 3, which is the input weights, plus 10, which is the bias. So in total, it will be 140. So now we have 140. So in total, we will have 173. Once you define this model with this set of numbers, we don't care if you are working with a text which is one A4 page or just one sentence or 2 sentences. We don't care, because the model complexity will stay the same, but number of activations will be different according to the size of the input sequence. If you have very long input sequence, we will have too much activations, but the model will stay the same, correct? Regardless of the size of the input sequence, and this is the beauty of this RNN. In fact, this is the beauty of RNN. So the model will not impacted by the size of the input sequence, but it's just the number of activations. And it's the same in CNN, right? But if you want to replace this one with MLB, no, it's another story, because when we are working with RNN, with multi-layer perceptron, I need to feed the whole text at once. I cannot divide it, because if you divide the text, you will not be able to predict the sentiment correctly. So if imagine that someone has a text about a movie, and in the first part he was positive, and in the second part he is negative. So it will be strange because maybe the first part will be positive and one sentence is positive and the rest is negative. So it's difficult to find a conclusion. So I need to apply the whole text at once, and it will be very difficult because some people write long text, some people write short text. I need to convert this text into a vector of numerical values. So I need to use some kind of word embedding, for example. So I need to convert it into a vector of numbers, which is a fixed size. So in this case, I will have a problem because people who are writing less, I need to fill in other places with zeros. We need to use this zero padding. And some people who are writing too much, for example, in this case, we need to use truncation. Should we use this truncation from the beginning or at the end? It will impact also my results. And also, we will lose information because when we use truncation, we will ignore the rest of the text. Maybe the first part was negative, but the last part is positive. So in this case, we were not very accurate. So it's much easier to work with recurrent neural network because we will not have such kind of problems. Please, if you have any questions, just ask it, please. And if you want us to stop also, just inform me. But if you want to take a break, we can take a break, but we can just take this example, for example, right? We will have this example and we can take a break. So this is an example. It's just sequence to one, right? It's an example of sequence to one. So I have a sequence or a text, a sentence, and this sentence consists of 3 words, for example, or 3 characters. It's A, B, and C, and I need to predict the next vocabulary, for example, or the next word. So my vocabulary consists of A, B, and C. It's like 3 words. For example, how are you, for example. So I need to convert this one into numerical. Each word should be converted into a numerical value. So I will use one hot encoding here to convert A into one hot encoding, B into one hot encoding, C. So it will be, this one will be converted into this one. So it will be, for example, 1, 0, 0. This B, it will be converted into 0, 1, 0. C will be converted into 0, 0, 1, for example. So now we have numerical representation for each word because my vocabulary is very short. I mean, it's just have 3 words. So I will convert it using one hot encoding. Now I need to define my X-train. So X-train will be consist of this sequence of text. The first sentence will be ABC. The second sentence will be BCA, for example. The third, it will be CAB. I need to use this one for predicting the next word. So when it's ABC, the next word, it should be B because the first word is A. When it's BCA, the next word will be C, right? The one in the middle. When the next word here, it will be A. So this is my data set. I have X-train and Y-train. I will build my model as we did last time. So the input, this input shape, a number of steps, it will be the length of my sequence, correct? So each sequence consists of 3 words. So I will use 3 time steps. But each word is represented by one hot encoding. So in the first activation, I will apply A, and then when I apply A is represented by this one hot encoding. So the number of features equal 3. Number of features equal 3. So first I will apply A, and we should predict the next word. It should be, for example, B, right? So we will train our model. We use this metric accuracy, categorical cross entropy, because it's I need to calculate the probability of the next word. Therefore, we use this one here. And this is as we did before. I mean, you can generate this figure also. So this is the input layer. So the input is 3 times 3, and the output will be 3 times 3 because the input layer does not have any parameters. For the simple R in the end, the input will be 3 times 3, and the output will be 10. Why the output is 10? Because we selected here number of units equal 10. In this case, we will try to calculate 10 hidden states. So the output from this layer will be 10 hidden states or 10 outputs. So the output will be 10. So the input to the dense layer, it will be 10, and the output will be 3 because we need to calculate the probability of the next layer. So we trained the model, and I try to test the model with those text A, B, C. And then when we feed it with ABC, we should predict B. We need to get B. When we feed it with BCA, I should get C. So this is the output from the dense layer. So I printed it. So this is the vector, first vector, which we will get when we feed it with ABC. And as you can see, this number is very small, close to 0. This number is close to 0. This number is close to 1, which means this output, it will be 0, 1, 0. So when I feed it with ABC, we should get 0, 1, 0, which means this one is B, right? When I feed it with BCA, we will get this number, which is 0, 0, 1. And the 0, 0, 1, it means it's C, right? This one, it's equal C. So in this case, when I feed it with BCA, the next word in my sentence, it should be C, right? So it's many to 1, right? So in this case, we do many to 1, and number of repetitions equal 3. So I try to unroll it to explain it for you. How many hidden states? It's 10 hidden states. So 1, 2, 3, 4, 5, 6. So this vector, it's 10 values. And this is the initial hidden state. We initialize it to zeros, for example. And in the first activation, I will apply A, which is 1, 0, 0. And we will calculate a hidden state. This is not the actual number, sorry. So this is H0, this is H1. So I calculated H1. And then we will do another activation, another repetition. But in this case, I will feed it with B, which is represented by 0, 1, 0. So the dimension of the input, number of features equal 3, because each input is represented by a vector of one hot encoding. So it will be 0, 1, 0, for example. And I will use H1 for calculating H2, correct? And at the end, I will apply C. And when we apply C, we will try to get H3. And from H3, this is the output, for example. This is my output, H3. I will feed it to my softmax layer, right? So the softmax layer, it's just one layer, which has 3 outputs and 10 inputs, right? So number of parameters here in this softmax layer, we need to predict next character, for example, what will be the next character. So when I apply A, B, C, in fact, this one should be B, so this one should be 1. I need to fix it. So it will be like this one. If you want to calculate parameters here, number of parameters of this softmax layer, it will be 3 times 10, because I have 3 outputs, 10 inputs. So number of parameters here, it will be 3 multiplied by 10 plus 3. Number of parameters here, we don't care about number of repetitions. It's not our business, in fact, because number of repetitions, it's just a mean number of activations. It will take calculation time, but it will not impact number of parameters in my model. If you want to calculate number of parameters, I have 10 states. So number of recurrent weights, it will be 10 times 10, right? Number of input weights, it will be here 3 times 10, 3 times 10. And because I have 10 units, so number of bias will be 10. So it will be 10 multiplied by 10 plus 3 multiplied by 10 plus 10. If you want to, I mean, this last example, it was sequence to 1, correct? This example here, it's a sequence. It's similar to, because I need to predict the next letter or next character, for example. So it's a sequence to 1. So I will apply the sentence A, B, C, and the number of repetitions, it will be 3, because I need really to do 3 activation, because my sentence consists of 3 words, A, B, and C. So we will do 3 activations or 3 repetitions for calculating the next character. And at the end, when we will apply A, B, and C, we will be able to predict that the next letter was B. Next character in this sentence was B. If you want to convert this one into sequence to sequence, so in this case, I need in fact to get outputs from those hidden states. So I need to feed this one. I need to get access to this one, H2 outside. I need to get H3 outside. So I will have H1, H2, and H3, and maybe apply H1 each time to a dense layer. So I just need to, if you want to convert this one into sequence to sequence, so it will be the same example. So for example, but we will change the train set, because if the input is ABC, I want the output to be BCA. So I need to predict the next sentence, right? So I have a sentence which is ABC. What will be the next sequence or next sentence? It will be BCA. So in this case, I need to predict this. So I just need to use return sequence equal true. When you use train return sequence equal true, we will be able to get access to the hidden states each time, right? We will get access to this hidden states each time. And in this case, we will apply this hidden states to this softmax layer, and we will get okay, so I can get we will get when input for example is, yes, I mean it's sometimes it's so for example when it's A, B, and C, for example, I need to get access to this hidden states, and I need to apply this hidden states to the softmax layer and predict what is the character. I mean, what should be the input now? If the input is A, what should be the output here? Of course, it should be B, right? When the input is B, what should be the output? It should be I mean the next sequence. So when it's A, B, and C, I need to predict. When it's A, B, and C, I need to get the next sentence is B, C, A, B, C, A. So in this case, when I feed it with A, I should apply this hidden states to this softmax layer in this activation, and I need get B, for example. When I apply B, I will use H2. I will apply it to the soft layer, the softmax layer, and I will predict C. When I apply C, I will get A. So in this case, the input will be a sequence and the output will be a sequence, just like machine translation. Yes. So so this return sequence equal true. You will be able to get access to the hidden states in each repetition or in each activation, right? And it will also, what will be the impact here? What will be the difference? In fact, it will not impact the number parameters, but it will impact yes, it's just the structure of the model, but the number of parameters should be the same, right? So return sequence equal true. It means you want to get access to the hidden states in each activations, because I need to generate sequence to sequence, and it's the same category. We will use the same loss function, exactly the same, no change. But when you return the sequence equal true, in this case, you will be able to generate sequence output, right? But of course, you need to change your training data to be sequence to sequence. So I just trained X train, Y train, it will be sequence to sequence, which means the input will be one sentence, and I want to predict what will be the second sentence, for example, right? Number of parameters will be the same, no change, no change. This is if you want to get access to the outputs from each, if you want to get access to the outputs from each, from the recurrent layer, I need to build a new model. Do you remember? Okay, model. I need to define a new model, this intermediate model. So this is my original model, which we will train using this data set, for example. And if you want to get access to, to the output from the recurrent neural network, right? Recurrent layer, you need to define this intermediate model or temporary model. And this model, the inputs will be the input to my model, as we did before. Do you remember when we want to plot those intermediate values? And the outputs will be the output from layer 0, which is the recurrent symbol R in the layer. So you just need to define a model if you want to get access to those return sequences. We did that before with C and N. If you want to do it with R and N, it will be the same, no difference. I need to define a new model, temp model, and I will use this model API. The input to this model will be the input to my model, original model, model.input, and the output, I need to get access to this layer. So the output will be model.layers 0, which is a recurrent layer, right? You should expect that, and just do this model summary, for example, number of parameters will be the same, 140, there is no change. But the output from this model will be 10 values, right? So now when we try to print the output, so the output will be this temp model. Don't predict, for example, I need to predict, so I need to send a text or a sentence. I will send this X test 0, which is the first sentence, and I will try to plot the outputs. So the outputs in this case, it will be 3 vectors, one from each activation. So this one will be the first one when we apply A, correct? When this one when we apply B, this one when we apply C, right? So, and it's 10 values. So it's 0, 1, 1, 2, 3, 4, 5 times 2. So it's 10 values each time, which is the hidden states. So those are the hidden states from each repetitions or from each activation, for example. So it will be something similar to this one. When I apply I, for example, I will get access to those hidden states. and I will use those hidden states for, sending it to a softmax layer for predicting maybe the, the next sentence or the next word, for example. So in this case, we will be able to get access to those 10 values, the hidden states, and each time we will apply those hidden states to the soft, not only the last value, because last time we don't need to get access to those hidden states. We just apply the last hidden state. We do those repetitions or activations, and we will apply the last hidden states to my softmax layer to do sentiment analysis or predict the next word, for example. But if you want to convert it into sequence to sequence, in this case, we need to use return sequence equal true. And in this case, we will get access to those hidden states in each activations, and we will apply those hidden states directly to the softmax layer and predicting, the next word, for example. So in this case, the input will be sequence and the output will be a sequence. Okay, so yeah, maybe if you want to, we can stop here and you can just take some time because it's 1 hour. And do you would like to take a break?
Yeah, sure.
Okay, so you can take 10 minutes break and start back again. Please sharp at 10, maybe 10:45, maybe 10:50. Okay, we can start again at 10:50 because I hope if we can finish the rest of the slide today. Okay, so see you soon.